In this presentation, I'm going to talk about the deep residual architecture, one of the most popular neural network design that published in 2016. The outline of the presentation is as follows. Now I will start with the motivation behind the ResNet and residual connection. The question that they start off is by trying to answer what happens when we try to stack a deeper and deeper layer on a plain convolution neural network. In other words, can we just continually stack deeper layers and the performance will just do better? So the answer is no. So let's take a look at what happens when we get a deeper network. Here's the author comparing a 20 layers plain neural network with a 56 layer plain neural network. From the figure, we can see that 56 layers network has higher training error and higher testing error. However, we knew that if we have a deeper network, the network will have more parameters to train and it will start to overfit at some point of time. When the model is overfit, we will expect to have a very low training error rate and high test error. But what's happening here is that the training error of the 56 layer network is doing worse than 20 layers network. Therefore, they conclude that this phenomenon is not caused by overfitting. So they hypothesize that the problem is not caused by the overfitting, instead it is an optimization problem, where the deeper networks are just more difficult to optimize than the shallower networks. The reasoning behind this is that the deeper model should be able to perform at least as well as the shallower models. So for example, in the diagram, if we make the deeper layer to copy all the landed layer of the shallower network and having the rest land the identity function, then the deeper network can precisely mimic the shallower network. Motivated by this, their solution is to make it easier for the model to land this kind of identity mapping. Their idea is, instead of learning to transform X via a neural network into X, which is an identity function, why don't we have X stay as X and then learn whatever we need to change? Basically, there's a skip connection the loop here where it will just take the input and pass it through as an identity. So the additional weight layer here will land the residual f of x and the output will be the input x plus sum of the residual f of x. The main idea is that the learning of the residual is much easier because the weight layers are usually initialized as small random number, and for that, in the case where the identity is ideal, the weight layer will just set all the weight to 0 and then we will just going to have an identity as the output. In other words, the identity function will be the default function in the residual block. Now let's take a look at the full ResNet architecture. Basically, it will begin with a convolution layer and then followed by the residual block which we introduced earlier. So the residual block here will stack on top of each other, and each of these residual block will have two 3x3 convolution layer which happen to be a good configuration that works well. Periodically, it will double the number of filter and downsample directly by convolution layer that have a strike of 2. Finally, it will end with the global average pooling and fully connected layer with softmax. They have created the ResNet with a total depth of 34, 50, 101 or 152 layers for ImageNet dataset. Now, let's zoom into the shortcut connection. For each of the residual blocks, the dimension of A's and F of A's must be equal in order to do element-wise addition. In the case where F of A's and A's are the same, the parameter-free identity shortcut can be directly used. However, if it is not the case, we need to do the dimension matching by either using the zero padding, which is parameter-free, or projection shortcut, which is done by one-by-one convolution filters to match the dimension. On top of that, for the deeper ResNet, in order to reduce the training time or to improve the efficiency, they have replaced the normal residual stretcher with the bottleneck residual module. The normal residual module has two 3x3 conv layers. However, the bottleneck module uses a stack of 3 layers instead of 2. These 3 layers are 1x1, 3x3, and 1x1 conv layer. So from the figure on the right, we can see that the 3x3 conv layer is to do the mapping, and the rest 1x1 conv layer is to increase or decrease the dimension. So the input will first pass through the first 1x1 conv layer to decrease the dimension, and then it will pass to the 3x3 convolution layer to do the mapping. And then finally, it will do the dimension increase by 1x1 convolution in order to make a identity shortcut connection from the input. So by doing so, they can reduce the computational cost. Now let's discuss about their experiment result. So let's take a look at the right figure. We can see that the VGG with the 19 layer network has a lot of parameters which need 19.6 billion floating point operation. In contrast, on the left figure, we can see that the residual network with even 152 layers only need 11.3 billion operation. So we can see that the complexity of the ResNet is much less than the old VGG network, even if the ResNet had much deeper layer. Moving on, let's look at the comparison performance between the plain network versus ResNet on the ImageNet dataset. If you look at the left, these are the plain network, and the deep network with the deep 4 layers simply has higher training and validation error. On the other hand, with the residual connection on the right, we can see that the trend is totally reversed. Now 34 layers with residual connection has a much lower training and validation error than 18 layers. This indicates that the ResNet is able to train deeper network without degradation problem. Next, they explore the different model and compare it with previously well-performed models. So from the table on the left, we can see that the deeper model outperform all previous baseline model and themselves if they went deeper and deeper. Therefore, we can see that the ResNet model benefit from the very deep models. Moreover, on the right table, they have built the ensemble model, which end up with the 3.57 error rate, which is better than human performance, and it end up taking up the ImageNet 2015 competition winner. Here, the result shows the classification error on the CIFAR-10 test set. Similarly, we can see that the deeper the ResNet we have, the lower the error rate we get. However, once we reach a certain depth, like for example in this case the 1202 layers, the error rate goes up again. So the question here is, was this caused by the degradation problems? The answer is no. So if you look at the right here, if you compare the 110 layer with 1202 layers network, we can see that the validation errors goes up. However, the training error is almost the same and is around 0. So we can conclude that now we have actually built a large enough network that is overfitting. And the fact that we go up again in the validation error is due to the fact that we are probably overfitting. So not only it enables us to build a deeper network, it effectively shows that this can get to a point where we don't need a deeper network anymore for the data set. So in this case, it's CIFAR 10. Lastly, they investigate the standard deviation of the responses. In this experiment, they try to compare the response magnitude of having and without the ResNet connection. So we can see that the response magnitude of the ResNet are significantly smaller than that of plain network, because the identity function is already doing most of the work, and each of these layers only need to learn kind of small functions. So it turned out to be accurate that it is reasonable to build a skip connection of identity mapping into the architecture. In conclusion, based on the residual net, they have won the first place in all ILS VRC and COCO 2015 competition. Finally, from the performance of the previous year's ImageNet winner, we can see that the depth is the key to get a high accuracy. Thank you, and this is the end of the presentation.